Good morning, everyone. Today we are presenting our design for a hybrid power generation system that combines the hydroelectric and also solar PV array technologies. So our goal is to provide a stable and continuous power supply for an industrial oil extraction machine and also nearby village. So this hybrid approach maximizes the reliability by using the river flow for base load and also solar energy to meet peak daytime demands. So let's take a look how we generate this power. For the hydroelectric component, we utilize the continuous river flow that will provide the gravitational potential energy from the headphone, then converted into the kinetic energy through a pen stock. It will strike the blades of the coupling turbine, cause the turbine to rotate, and this mechanical energy is then converted into AC power via three-phase synchronous generator that already chosen for its precise voltage and regulation. For the solar component, we have selected the high-efficiency monocrystalline panels. These convert sunlight directly into the DC electricity through the photovoltaic effect. So the system is particularly effective as its peak generation around the midday aligns perfectly with the peak operating hours of the palm oil processing facility. For the estimation of total power loads, the total power demand is 156.84 kilowatt. So this includes the heavy oil extraction machine, conveyor, pumps, internal facility loads, and also the power requirement for the 40 village household. For the size of generator, we have select a Kaplan turbine. So it was chosen because its adjustable blades allow for optimal performance in low head, high flow river condition typical for this type of application. So to convert this mechanical energy, we have sized the system with a three-phase synchronous generator. So this specific generator type was selected because it provides a stable voltage and frequency regulation that required for the heavy manufacturing machine and sensitive village electronics. So it also allows for precise excitation control to meet the high electrical demand. For the estimation of power generation for hydroelectric, the power generation is 130 kilowatt, while the power generation for the solar PV array system that will estimation of the 63 kilowatt power. So we also have account for the power losses that is 32.97 that caused by the rectifier, generator, and also inverter and the transmission line. So after calculate, we also balance the generation against the demand and also losses. We have maintained a positive power difference of 3.19 that will ensure the system remains stable even under load. Lastly, for the energy storage option, we use a battery energy storage for the hydroelectric to manage the flow. So the hydroelectric AC power is rectified to DC power, while the solar PV array system is regulated via the DC-DC converter to prevent overcharging. So this energy is stored in the electrochemical form using the lithium-ion battery banks that will allow us to capture the excess solar energy during the day and release it at night, ensuring that the facility and the village never face a power shortage. So that's all from me. Thank you.
Moving on to transmission and distribution. This section covers the transmission system designs, voltage levels, conductor selection, and protection devices. The transmission system transfers excess power from hydroelectric and PV solar sources to industrial lots and nearby village. The power first flows to the main distribution panel and then to the battery energy storage system, or BESS. Once the BESS is fully charged, excess power is applied to other locations. Since the BESS produces DC power, an inverter will convert it to AC. A step-up transformer increases the voltage to improve transmission efficiency. Higher voltage reduces losses over 10 km distance. Before reaching the factory and village, step-down transformer reduces the voltage to safer levels. Lastly, the protection system are also installed at both ends for safe operation. Two voltage levels are used for this power system, and these values are from the TNB standards, which are 415 volt as the primary voltage and 11 kilovolt as the secondary voltage. This medium voltage level is suitable for distance between 5 to 20 kilometers. After applying a 28% safety margin, a 300 kilovolt ampere step-up transformer is selected. For a step-down transformer, 150 kilovolt ampere is used for the oil pump factory and 112.5 kilovolt ampere for the village. Copper cables are used due to their high conductivity, durability, and corrosion resistance. Although 6 mm squared means the basic calculation, it is not suitable due to high voltage drop and poor mechanical strength. Therefore, a standard 25 mm square cable is selected. For medium voltage, by refer to the table 6.35/11 kV insulation, it is shown that the overall cable diameter is about 18.9 millimeters. An overhead ABC transmission line or aerial bundle cable is used because it offers high safety, durability, and reduced power losses. Reinforced concrete poles are installed in a 3-phase 3-wire system with a spacing of 80 to 100 meter and a height of 6.1 meters. The total cable length required is 31.5 kilometers since we use the 3-phase 3-wire system. Lastly, the system complies with Energy Commission Malaysia, TNB, and IEC standards. Safety devices including lighting arresters, earthing at every pole, cradle guards at road crossings, transformer tap changes, and a 300 AMP MCCB. Regular maintenance ensure reliability. The diagram shows the complete transmission and distribution network from power generation to industrial and village users.
Hello, I would like to talk about motor selection. For motor selection, we choose a 3-phase squirrel cage induction motor. As you can see, this motor is suitable for applications such as oil extraction machine using screw press system and oil transfer pumping systems. It was selected because it provides constant torque, high efficiency for continuous operation, and has a simple and robust design. In addition, it can operate reliability in dusty, humid, and high temperature environments, requires low maintenance, and is cost effective for long-term industrial use. Therefore, this motor selection meets the required performance, durability, and efficiency. This slide shows the motor rating and starting method. The motor is rated at approximately 80 kilowatts, which is suitable to support production about of 100 tons per hour. It operates at 400 volts and 50 Hz, which is a standard industrial power supply. In terms of protection, the motor has IP55 protection, making it resistant to dust and water, and Class F insulation, which allows operation at higher temperatures. The starting method used is start delta starting. This method reduces the high starting current, minimize voltage drop, and protects both the motor and connected mechanical components. This slide explains motor control and protection, which is essential to ensure electric motors operate safely and efficiently. Motor control manages the starting, stopping speed, and torque of the motor, while protection system prevent damage caused by electrical or mechanical faults. One common control method is the variable frequency drive, as you know, is VFD. The VFD controls motor speed by adjusting the voltage and frequency, allowing the motor speed to match the load demand. This helps reduce energy wastage and improve efficiency. For protection, thermal protection prevents overheating, overload protection avoids stalling and mechanical damage, and circuit breakers protect against short circuit. Overall, these systems improve energy efficiency, motor lifespan, and operational safety.
So first, we look at the rectifier, our hydroelectronic generator that naturally produces alternating current or AC. However, our battery storage requires the direct current or DC to charge. So we put the rectifier between these two components to perform that voltage conversion. But it knows about changing the current type. By supplying a controller DC output, we also isolate the battery from the generator frequency fluctuations. This will reduce the electrical stress on the battery and ensure we are making the most effective use of hydroelectric energy produced. Next, we have the DC-DC converter located between the solar PV array and the battery. Solar energy is inherently unstable. The voltage fluctuations occur constantly due to change in temperature and solar irradiance. So, direct connection would be both risky and inefficient. Therefore, we use a converter equipped with maximum power point tracking. This technology harnesses the best possible power extraction from the panels while regulating the voltage to a level safe for battery. This protects the system from overcharging and significantly extend the battery's lifespan. The last devices is the inverter. So the inverter is the gateway to our distribution panel. Since industrial equipment, motors, and facility loads run on AC power at specific voltage and frequencies. Therefore, the inverter converts our stored DC energy back into high quality AC. Beyond this conversion, the inverter provides critical power quality control. It regulates voltage and frequency to ensure that the power reaching the extension pumps or the nearby village is stable and safe. Now we go to enhancing system efficiency. This is to minimizing energy loss. The power electronics ensure energy is converted with minimal dissipation and high efficiency conversion to prevent the energy from being lost as excess heat. And then next, the optimized power transfer. Precise control of voltage and current ensures the maximum amount of generated energy reaches the end load. And then lastly, operational benefits. This is to reduce energy consumption and lower overall maintenance costs. Then enable to it enables equipment like extraction pumps to operate at the ideal rate conditions. And then moving on the last slide on my part, which is system reliability and thermal management. So the first one is heat reduction. Efficient conversion generates less waste heat, and then simplifying cooling requirement. Therefore, lower operating temperature to prevent the component failure and insulation degradation. Next, the component longevity to reduce thermal and electrical stress on batteries, converters, and cabling. This is to extend the lifespan of the battery by preventing wasteful charge or discharge cycle. Lastly, power quality and stability to prevent issues such as overheating and excessive current draw. Ensures a reliable and stable power supply for both the industrial facility and nearby community.
Hello everyone, today I will present the system analysis and technical verification for our hybrid power project in Sabah. My focus is to prove that our design is not only functional but also safe, efficient, and compliant with national standards. To begin, we map the system using 4 critical analysis nodes as shown here in figure 5.1. Node A is our generation bus where hydro and solar power combine. Node B is the industrial hub powering our heavy VFD controlled motors. Node C and D represent the transmission and the final village distribution. Our total system demand is 1000 kilowatt. We have designed the system at 0.8 per unit PU loading. This 20% safety margin is vital. It ensures that when the large palm oil extraction motors start up, the village at Node D doesn't experience a voltage drop or blackout. Now, let's look at the engineering method that secures the system. First, for safety, we dive into the engineering verification. We calculate a worst-case fault current of 8.35 kA based on our full load current of 417.36 amperes. To ensure the absolute safety of the facility, we have specified circuit breakers with a 36 kA breaking capacity. This provides an excellent safety margin for our infrastructure. Next, for efficiency, we address the power factor. By installing a 422 kV capacity bank, we improve the system efficiency from 0.8 to a high 0.95 power factor. As you can see in the power triangle, this significantly reduces the wasted reactive power, allowing our hydro generator to run cooler and last longer. Finally, our use of passive LC filters ensures that harmonic distortion from our power electronics stay below 5%, keeping the power quality clean for the community. To conclude, this design is fully compliant with Suruhanjaya Tenaga Safety Standards and the Sabah Renewable Energy Enactment. By replacing the cell generators with this hybrid solution, we eliminate 2,500 tons of carbon emissions every year. We are providing a zero-emission, stable, and reliable power source that supports both the local industry and the community's future. Our analysis proves that this system is technically verified and ready for implementation. Thank you for your time.